Hello everyone and welcome to this Geographic Information Systems course. And today we will continue on the discussion about various techniques to generate digital elevation models. So, two parts we have already completed. Now, this is the last part about the digital elevation model generation. In this one, as you know that we have discussed how to generate digital elevation model using stereo pairs, and that is in implying photogrammetric techniques. I gave examples of spot or cartosat satellites also, completely remote sensing based method. Another method also is the radar pairs or in implying SAR interferometry. Though SAR interferometry itself has become a big subject, but from our course point of view, I very briefly discuss about this. And then also I discussed about the LiDAR technology, which is again remote sensing based technology. And now we are in this discussion, we are going to focus on how we can exploit thermal infrared data, especially of a hilly terrain, for generation of a digital elevation model. Why specifically for hilly terrain? As you know that ground surveys are relatively easily possible in areas which are plain, but ground surveys, field based surveys in hilly terrain are really challenging, very difficult, and sometimes many areas are completely inaccessible to humans. And therefore, generating a digital elevation model of a hilly terrain, for example like higher Himalayas, is very difficult. And therefore, this technique can really help us to exploit this thermal infrared data and the relationship which we are going to discuss to generate a digital elevation model. Relatively coarse resolution thermal infrared data is available from NOAA AVHRR data, and NOAA is the name of satellite. AVHRR is Advanced Very High Resolution Radiometer. This though it is in name it is said high resolution, but 30 years back that was definitely high resolution, but compared to today's what the data available, it is not really high resolution, it is 1 kilometer spatial resolution, but in a in an entire day it can cover the same terrain twice in a day, and that is very advantageous from that point of view. So, though the resolution is less, but it can provide still good quality of data, and this is the satellite or this is the sensor. NOAA AVHRR sensor is the most used data world over in the field of remote sensing, because data since beginning has been free, and anyone can have their own satellite earth stations because data is in public domain or in direct broadcasting mode. So, if you are having your own satellite earth station, you can directly get the data of your area and surrounding from this satellite. And now as you know that there is a inverse relationship between temperature and elevation, and that means that as we go higher in altitude, we get less temperatures, and this relationship can be exploited for this implying the thermal channels, because NOAA AVHRR data is having 5 channels data, and there are 2 dedicated channels which are thermal channels. So, those channels can be exploited to create a to find out this relationship, that is the inverse relation, and then same can be used. And since 2002 at IIT Roorkee we have been operating this NOAA AVHRR satellite earth station, and using our own data set, basically we developed a digital elevation model for a hilly terrain, for a very difficult and challenging terrain, and very successfully we could demonstrate that this can be done. And we also made a comparison with USGS data, and for some controls also we used that one also. So, as you know that USGSDM, which is available free of cost, initially it was developed, also we discussed in the initial discussion related with the digital elevation model generation, and that it was developed using 250,000 survey topo sheets and their contour lines were digitized and then later on interpolated and surface were generated for entire globe. So, this is a global digital elevation model, but compared to today's what is available, it is again a coarse resolution 1 kilometer. But I would always insist that always it is not required for anyone to always go for high spatial resolution either remote sensing data or digital elevation model. And because if relatively it is coarse resolution data, the area which it covers is really very large or very huge compared to very high resolution data. For example, if I give you example from NOAA HRR, in one scene you can cover about 2800 kilometer width, or the swath is 2800 kilometer. And if I go for 1 kilometer resolution satellite image, then in one swath I cover only 11 kilometer of the part of the earth. So, that makes the difference, from 1000 meter to 1 meter. If there is a inverse relationship between the spatial resolution and swath. So, coarser the spatial resolution and wider the swath, and vice versa is also true. And this USGS DM for entire globe is consisting of 33 tiles. Spatial resolution I have already discussed, and these are numbered like this, and like for northern hemisphere, eastern hemisphere, and likewise. So, for India, this is east 60 degree, and that is the longitude, and north 40 degree, that is the latitude, and this is the corner coordinate for entire India tile. Now, if you see the specifications about NOAA HRR, as I have already said that the spatial resolution is about 1 kilometer, that is 1000 meters, and it depends where it is located, but nonetheless you can acquire at least 4 images per day, but the same time the same area can be visited at the same time at least once in a day, in a daytime and another in night time. Why night time it is possible? Because it has got the thermal channel, and these thermal channels can be exploited to generate digital elevation model, which is what we are going to see. So, what we need basically a cloud free nighttime thermal data. Now, if somebody is trying to generate a higher spatial resolution digital elevation model employing this thermal remote sensing technique, then there is a way also. And nowadays Landsat OLI series, that is Landsat 8, is also having thermal channel, and the data is available at 60 meter resolution. So, from 1000 meter you can come to 60 meter, and then still you can exploit it, this inverse relationship between altitude and temperature, and you can try to generate a digital elevation model at 60 meter resolution as well. Anyway, if we discuss the methodology part, so you require a cloud free nighttime scene. Why nighttime? Because solar heating differentiation is minimum in the nighttime, and luckily these satellites, they overpass in the early morning local time, maybe 2 o'clock or 3 o'clock. So, at that time the effect of differential solar heating is minimum, and therefore it is always good to go for nighttime thermal data. One may think that how in nighttime I will detect the clouds, because all channels in nighttime will not work, at least 2 visible channels of NOAA HRR. But there is a infrared channel and these 2 thermal infrared, and they are still operating, they will also record. So, employing the thermal infrared, the infrared channel, one can very well detect clouds. So, it is easy, it is not difficult to find out the nighttime cloud free scene from NOAA HRR data. However, when I gave this comparison with Landsat, then acquiring nighttime Landsat data that is not available generally on their portals, but I am sure that if you make a special request to them, then it is possible to even acquire nighttime data from Landsat, because they are not acquiring the data, but satellite always overpass in night time in that area. So, it is surface temperature computation is done after acquisition of data. Now, digital elevation model of the same resolution, that is USGS topo resolution, and then of course, you require the same corresponding DM. Why it is required? Because we want to have some values about elevations, and especially the minimum value of that area and maximum elevation value of this area. And therefore, the best resource is a USGS DM, which we can definitely use just for having these two values for the area. And then of course, you require DM to image registration. So, that means you are working for the same geographic extent. If you want to see the results and compare with DM and image, you have to plot a scatter plot to find out a relationship, which I will show you, and then you can further study that AVHRR and DM generated from two different techniques. You can do a visual inspection or a visual analysis, and of course, one can also perform statistical analysis. So, and this is on the left side, what you are seeing is a NOAA derived digital elevation model, and on the right side what you are seeing is USGS DM. Both are having 1 kilometer resolution, as visually you would find that there is hardly any difference. But when we will see statistically, there will be some and since these minimum or maximum values are coming from USGS DM, so therefore both are having the same minimum and maximum value, because using those values, this output of this USGS DM has been is rescaled. Now, as you visually you can see, there is hardly any difference, but when we plot a scatter plot, still we find that there is a very high correlation visually in this one. So, on one side you are having elevations derived from USGS, and other side you are having the brightness temperature derived from NOAA data when you plot, and this is what you see. Also, for different elevation ranges, when you perform further analysis, you find that the histogram pattern is almost same. That means, in almost each elevation ranges, it is matching quite well with the USGS DM, as you can also see very carefully. Now, when we perform this correlation analysis, we find that of course, minimum maximum would be same, because USGS DM minimum maximum has been taken to rescale NOAA DM, but a mean value here is a little higher than NOAA, and same with standard deviation is relatively low, and this is higher in that sense. And when we do this correlation, we find a very high correlation, that is 0.967334, which is almost 1. So, it is having very high correlation with your NOAA and USGS DM, and therefore, it proves that while employing thermal images of night time from any satellite, if we need just for the same area, we need a reference for two elevation values, that is minimum and maximum. Once those are there, we can rescale the entire thing and can generate a digital elevation model of very good quality. But again, there are some, because no technique is ever perfect or universal. Every technique will have its own issues. So, one issue here is, if there is a dense vegetation cover, you may not get that good results. So, that is one limitation. Of course, you require, for better results, you require nighttime images, but if they are not available, then you have to resort to the daytime thermal images, which may bear this differential solar heating issues. So, higher spatial resolution, as I have said, from Landsat ETM plus or latest series Landsat 8 OLI series, you can create a digital elevation model. And limitations, I have already said that because since it is a relatively coarse resolution satellite image, which is NOAA HRR. So, the accuracy of georeferencing has to be very high. So, that is one essential requirement. And second is the best applicable only in a highly rugged and natural terrain. So, natural, more emphasis I am giving on natural terrain. Like in higher Himalayas, it is more or less undisturbed by humans and it's a natural terrain, and therefore you get very good results. But if someone is trying to generate a digital elevation model where a lot of human interventions are there, then probably you may not get good results. And of course, you need to have some ground values or some elevation values for your reference. So, that those for that there should not be much problem. These are already available. Now, the other thing is that the seam between two tiles in USGS DM may enhance the error part. That means that because as you know that USGS DM developed using survey topo sheets of different countries. So, sometimes you would find that even for the same country they use two different projections or spheroid, and that has created a seam between two tiles or two topo sheets. So, if that seam is visible in your USGS DM and the same USGS DM you are employing and trying to compare with your thermal data driven DM, you may get this problem. So, if visually you can inspect whether there is a seam in the DM of USGS which you are going to use, in case you are using NOAA HRR data. But in case you are using Landsat thermal data, then the scenario can be little different. Now, this part we will be discussing further extensively, but for time being sources of DMs which we have already discussed, that you imply the survey of India or survey topo sheets and digitize contours and then do the interpolations and you get a digital elevation model. And these are the free resources which the topo sheets based USGS DM which I have already discussed. So, free resources is 1 kilometer USGS DM. SRTM was also developed initially for 1 kilometer, 90 meter, and now also 30 meter is available. Now, there might be some problem with the free DMs. The first problem is having seam, at least we have observed in case of Indian tiles. So, these seams, because of different map projections or different spheroids between two topo sheets, adjacent topo sheets, there might be some seam. So, that may give you some poor results. Another one is earlier 90 meter SRTM had voids, that is filled with no data. Though these voids were replaced with the coarse resolution and elevation values like coming from USGS DM 1 kilometer. So, you may encounter this problem also, though you may get void free data, but for it is saying it is void free, but in fact those voids have been filled using relatively coarse resolution cells, and therefore the problem will still persist. So, though as I have said that the voids can be substituted with the low resolution DM, but will have some problems. Let me give you some example of voids. This is Himachal Pradesh, and what USGS DM 1 kilometer we are having, and when we compare with the 90 meter SRTM DM, what we find that these colored one, dark maroon color which you are seeing the areas or cells, they are nothing but the voids. Because remember that SAR interferometry technique was employed in SRTM, INSAR technique was employed in to generate digital elevation model of SRTM, that is shuttle radar topographic mission. Now, this SAR interferometry technique, when we go for glaciated terrain and a snow covered area, there might be some problem with that data because of high water content, absorptions of energy due to high dielectric constant and other because highly rugged terrain, and therefore you may get these dark maroon areas at least in this display in this display, or they are having the no data value. Here the no data value has been assigned -32768, and therefore you are seeing this one. So, employing this 1 kilometer USGS DM, and we have filled this one or replaced these no data values with the USGS DM 1 kilometer, and still you can create a digital elevation model at 90 meter resolution, except for those void areas, and you do not see any void at this scale. But if you start zooming it, you may find some problems, like here what you are seeing USGS DM, the seam part which I was mentioning here. See this seam, it is very clearly seen here. So, that means these are this area belongs to the two topo sheets, part of two topo sheets. SRTM DM 1 kilometer resolution, this DM has been used, or cells of this DM has been used to replace your that one of voids of 90 meter DM. So, obviously, because 90 meter DM is having much higher spatial resolution, and therefore, it looks much better and informative than 1 kilometer resolution. So, similarly, one more example about 90 meter, this is again corrected. Corrected means void filled DM which is there, but in plain areas the voids are very little, but in case of hilly areas sometimes you may encounter lot of void. So, nowadays already void free SRTM DMs are available not only at 1 kilometer 90 meter, but also at 30 meter for entire globe. Now, just in the summary, what I am bringing here is DM sources of different applications at different scales. Topographic based maps I have already discussed, and there are some solutions are available which can be used for flood modeling, landslide mapping, and for coastal mapping, other details and so on. So, it depends on what scale you are going to work and what is going to be your target. Accordingly, you can choose the scale, also accordingly you can choose the different spatial resolution. One important point here is that you are seeing two resolutions, one is horizontal, another one is vertical for resolutions. The reason is the least count in vertical scale generally is 1 meter, whereas spatial resolution, that is in the horizontal scale, that is X and Y. So, X and Y may have a 30 meter spatial resolution, but the Z value may have least count of 1 meter. So, there we can say that is having a vertical resolution is 1 meter, and therefore, a DM generally is having two resolutions. One is spatial resolution, that is the horizontal one, another one is the vertical, which is about the height. So, generally there is a difference. Spatial resolution is always less than what you are having vertical resolution, and so one has to be really careful while bringing these issues, and the rest of the techniques are there which are based on different techniques, and ground based radar, and like SRTM, Ester DEM. This is Ester is again stereo data based, which has been created for entire world, available free of cost at 30 meter resolution. Spot you can generate by your own, but this Ester GDM or global DM, world DM is available free of cost, and of course, the Cartosat is also available at 30 meter resolution. So, lot of digital elevation models derived, generated using employing different remote sensing techniques are now available at different resolutions, and many of them are also available at 30 meter resolution, like SRTM, like Ester GDM, like Cartosat, all are available at 30 meter resolution also. So, by this we are having lot of choices. Before you start using any digital elevation model or decide to use any digital elevation model, the best thing is to assess the quality, whether it is having good quality or not, and that we will be discussing in future lectures. And by employing those techniques, you can assess the quality of your DM of your area of interest, and then employ for further analysis. So, with this I close this discussion. Thank you very much.